Okay, before we move into the topic of linear regression and the least squares regression line, I want to talk about this idea of R squared. We've already studied linear correlation and just the idea of the correlation coefficient R, but the value of that same correlation coefficient squared has very specific meaning to us in regards to correlation. So I want to go through this activity that normally we would do in class in groups. It's kind of going to be difficult to do in the remote learning setting. So I'm going to walk you through this using the Edpuzzle as our guide. So the first thing we're going to do is take 5 points, and I've intentionally used these specific 5 points. You'll see as we unpack the activity in terms of the amount of error that's there and the way we'll be able to articulate the meaning of R squared. So the first thing I'm going to do is I'm going to plot these 5 points. I'm going to use Desmos software, which is a free online graphing calculator that you all would have access to. So I'll show you how to use that. But I'm going to take these 5 points and I'm going to plot them in Desmos, and then I'll walk you through the next step. So if you wanted to use Desmos, you can follow along with this. We're going to come up here to the top and the plus sign here, and what we want to do is add a table. So in the table, I'm going to add those same 5 points that we have in our activity. The first x coordinate is 1, and the y coordinate is 2, and then we have 2 and 4. We have 3 and 6. And just when we think everything is following a certain pattern here, we have 4 and 8, and then we're going to deviate from that. We have 4 and 8, and then we have 5 and 15. Otherwise, this would be, all these points would live on the same line, and we wouldn't have much of an activity here. So I have my 5 points plotted over here on my coordinate plane. I'm going to drag this in so we can see it. And 515 sort of comes off of the graph a little bit. So the first part of the activity here presupposes, suppose we don't know anything about the behavior of x, and what we want to do is estimate y. How would we do that? Well, we'd go back to chapter 1, and one of the ways that we estimated any variable is by taking the mean. So I would take those 5 points, 2, 4, 6, 8, and 15, and I would average them. And when I average those points, I get a y bar, or an average of 7. So when I come back here, in my y2, I'm going to go ahead and plot a function. So expression, we want to add y1 equals 7. Actually, correction there, I don't want y1 equals 7, just y equals 7. So if you can see here, this horizontal line coming across my screen at y equals 7. And now what I'm going to do is I'm going to screen capture this. I'm going to bring it into my whiteboard so we can work with this for a minute and talk about the amount of error that we have in this particular model. So if I wanted to use y equals 7, that's this line right here. This is where y is equal to 7. To estimate the different y values, we can see I'm going to have a substantial amount of error here, right? Here's the y value here is 15. So 15 minus 7 would be an error of 8. Here the y value is 8, right? So 8 minus 7 will be an error of 1. Here the y value is 6, so 6 minus 7, this would be negative 1. Here the y value is 4, 4 minus 7 would be negative 3. And here the y value is 2, 2 minus 7, that would be negative 5. So maybe you remember this or not, these are our deviations, right? So I have a deviation of positive 1 and positive 8. That's a total deviation of 9. And then my negative deviations are all add up to negative 9. So if I just add the deviations together, I can't really average them. They're always going to add to 0. All right, so what we do in this case, and this is how we calculated standard deviation, we're going to square these. So this is 8, so we're going to go 1, 2, 3, 4, 5, 6, 7, 8, and I make a square, okay? And the area of this square is going to represent error in my model, okay? This is a square of 1. It doesn't really matter how I orient the squares. Okay, this is another square of 1. This is going to be a square of 3 squared, which is 9. And then 5 squared, 1, 2, 3, 4, 5. Doesn't matter that they overlap, okay? But what we find is the total error in this model, if I come back to my table here, we're taking our y value, which is in this case 2, minus 7, and we said that that was negative 5. We're going to square that, so that's 25. Okay, 4 minus 7, that's negative 3, right? We're taking the y value minus the average, which is 7, and we square that, that's 9. 6 minus 7 is negative 1. We square that, that's positive 1. 8 minus 7 is 1. We square that. And then finally, 15 minus 7 was 8. We square that is 64. If we add all of these up, the sum of these squares, 25 and 9 is 34 and 36. They're going to add up to 100. You'll see later on in the activity, I'm using that value intentionally because we want to use the concept of a percentage to articulate what r squared means. Okay, so what if we just computed? This is the sum of the squares of the error when using y bar equals 7 to predict y. Okay, so it's the best we have if we don't have another variable. But what we find here is that we do have another variable. Okay, when we invite the x variable to the party and use that to predict values of y, this is the model we come up with. Y hat, that's what we use to make predicting y's, equals 3x minus 2. It's the slope-intercept form of equation of a line, slope of 3, y-intercept of negative 2. So now I'm going to go back to Desmos. I'm going to plot that line and see if we have a little bit better model. So now when I go back to Desmos, now I'm going to use y1. I'm going to plot the function here. I'm going to add a expression, y1. And I use the tilde symbol here. This is shift and an apostrophe, so that's approximately. And we want to say 3 times x1 minus 2. And that gives us what we call our least squares regression line equation. Okay, and I'm going to explain in a minute why we call this the least squares regression line. Notice that Desmos also gives us a value of r squared equals 0.9, and then our correlation coefficient r, which we've already looked at, is 0.9487. So this tells us right away, 0.9487, that we have a strong positive correlation, which we could also see by looking at the graph. Okay, so I'm going to take this and grab a picture of this into my whiteboard as well. So you recall when we used just y equals 7, we had this sum of the squares of errors that added up to 100. So let's clear this, and now let's bring in a little bit better model. Okay, the least squares regression line. All right, and let's go ahead and do the same thing. I'll use a different color here, but let's do the same thing. Let's look at the error in the model. So when x is 1, the y value, the actual y value was 2. But the predicted y value is 1, right? So we would be here. Here they're the same number, okay? Here we're below the line, so our prediction was too high. Here again our prediction is too high, and here our prediction is too low. But you notice the error in my model here is a little bit different. It's gotten smaller now that we use the least squares line. So I'm going to do the same thing. I'm going to square all these errors so visually you can see what's happening here. And then I'll do the same thing. I'll have the sum of the squares of the error in this model. These two squares have an area of 4. This has an area of 1. This will have an area of 0. Okay? And then we can sum them up. So let's go back to the worksheet, and you can see algebraically what had just happened here. So remember, what's my predicted y value here? I use 3x minus 2. So the predicted y here would be 3 times 1 minus 2. Right? So I'm taking this x value and plugging it in here into my equation. 3 minus 2 is 1. Okay, and then down here we have 1 squared, which is just 1. Do the same thing here. 3 times the x value, which is 2, minus 2 is 4. So 4 minus 4 is 0. Okay, when we calculate here our distance or difference between the two, right? Our actual y value here was 2, so 3 times 1 is 3 minus 2. So this was, we go back and look at the graph, so you can see here, positive 1. Right? So I take the actual y value, which is 2, minus the predicted y value, which was 1. 2 minus 1 is 1, and we square that. Here we have 0, that's 0 squared. Okay, so here what's our predicted value? 3 times x, 3 times 3, minus 2. So 9 minus 2 is 7. We take our actual minus predicted. 6 minus 7 is negative 1. And then down here, we're squaring that negative 1, right? Which is just 1. 3 times 4 minus 2 is 10. 8 minus 10 is negative 2. And then we square the negative 2, which is 4. Okay? And then finally, 3 times 5 minus 2 is 13. And then here we have 15 minus 13, which is 2, and then 2 squared. So all of these values here, we have 1, 0, 1, 4, and 4. You can see them graphically on my whiteboard, right? 4, 4, 1, 0, okay? So what's happened here is we've drastically reduced the amount of error in the model. It's gone from a sum of the squares of 100 to a sum of squares of only 10. Okay, so the same thing. This is the sum of the squares of the error in our least squares regression line model. Okay, see how it's been reduced. So it may seem like an inflated value, but one of the things I want you to be able to see is that it's sort of necessarily inflated, because if we wanted to find the average error, we can't. We can't do it with standard deviation. They always add to 0. And these errors here, we call these our residuals. All right. These vertical lines, if a point lives above the least squares line, it's a positive residual. If it lives, so this is a positive residual, this is a negative residual. And it's just like our standard deviation. There's going to be positives and negatives, and they're going to add to 0. That's a characteristic of the least squares regression line. Another characteristic of the least squares regression line is the means of y, which we know is 7 already, and the mean of x, which if we were to calculate it, we would find is 1, 2, 3. So x bar is 3 and y bar is 7. That point always lives on the least squares regression line. Okay, the average of the x's, and we can go back and look at them. What's the average of these x coordinates? 1 plus 2 plus 3 plus 4 plus 5, right? If we add those up and divide by 5, we get an average of 3. So that point, x bar, y bar, always lives on the least squares regression line, and it is the one line that has the smallest possible value for these squares of errors. And we can see that if we go back to our applet that we explored in the first section. So let's look at the last part of our worksheet here. What did we have? We had the sum of the squares. We're going to express this as a ratio. When we used our better model, the least squares regression line model, our error went from 100 all the way down to 10. So this would be a ratio of 10 out of 100, right? If we completely ignored anything, any behavior with the x coordinates, we get an error of 100 by using the mean. Okay, so which of the following best describes this proportion? The proportion of how much error there is in the least squares model with respect to the error in the mean model. It's exactly what that means. Okay, this one says how the proportion of how well the least squares regression line model fits the data. I put that in there on purpose because I want to talk about a misconception of how people will oftentimes articulate R squared. We don't want to fall into that trap. So here I give away, spoiler alert, the correct answer was A. How would we compute R squared from the proportion of the model? Well, R squared is going to be 0.1 or 10%. I'm sorry, 0.9. Oops. All right, so let's just back up for a second. We want R squared to measure how closely our observed values fall to the least squares line. So 0.1 wouldn't articulate that very well, right? So how well does our model work? Well, we started with 100% error with the mean. And what did we do? We took away 90 or 10% of that. So our model went from 100% error to 10% error. Okay, so R squared would be 1 minus that 10%, or 0.9. Okay, so we went from 100% error. If we don't pay attention to x, when we pay attention to x, we've reduced it all the way down to 10. So what's left is 90% of the variation in our y variable can be explained by the x variable. So we take this ratio, R squared, it's 1 minus that percentage, right? We had 100% explained error. All right, we reduced that down to 10%. Okay, so it's the percent of variation in the y variable, okay, explained by the x variable. Okay, so remember, we want to always keep this in context. Like maybe our y variable is weight and our x variable is height. Okay, so always it's the percent of variation in the response variable. So you can always keep that in context. Explained by the explanatory variable. And this is our definition that we always want to use for r squared. It's the percent of variation in the y variable that's explained by the x variable. Okay, what it's not is a percent of accuracy. Okay, so for example, if we look at this least squares line, its percent of accuracy is only 20%. If we're trying to say how often it predicts it, there were 5 points and only one of them was predicted correctly. So don't ever try to think that r squared is the percentage of accuracy of your least squares line. It's the amount of variation in the y variable that's explained by the x variable using this least squares model. When we ignored the least squares model, when we ignored what's happening with x, we had a total sum of squares error of 100. Once we invited x into the mix and used it to make a least squares line, we reduced that from 100 to 10. So that means that our unexplained error, there's still unexplained error. This is unexplained, this is unexplained, unexplained. But it's now 10 instead of 100. So our least squares regression line model explains 90%, okay? 90% of the change in y that's happening using x. That's how we want to articulate this concept of r squared. I believe it's one of the more difficult topics that we tackle in this chapter, so I wanted to take time in the Edpuzzle to look at this.